Hi everyone, here we continue to solve additional optimization problems, and the one I have on the screen right now is similar to some of the problems we solved in the past segments about the box with the length plus girth being a specific number. But for this one there's an extra twist. Instead of length plus girth, they're saying that the length, width, and height, the sum of those three dimensions, has to be less than or equal to 192. And for the largest one, you can assume it has to be equal to 192. So instead of length plus girth, you have length plus width plus height being equal to 192. And in this particular problem, they also indicate that the length is twice the width. Okay. So to get the maximum volume, what should the dimensions be? So if we look at the figure here, so basically the length is twice the width. So if I call this side W, this side will be twice that amount, so 2W. And for the height, you can call it Y or H. So it is given that the sum of these three dimensions must be equal to 192. So length plus width and height, so 2W plus W plus H is equal to 192 for this problem. And 2W plus W is 3W, so 3W plus H is equal to 192. And once again, we're supposed to maximize the volume, so there you multiply the three dimensions, 2W times W times H, so there you're going to have 2W squared times H is the volume function that we need to be maximizing. And you may see the rest of the steps are going to be very similar to the last few examples. So from this equation, you could solve for H equals 192 minus 3W, and then you're going to come here and plug that in for H. And when you do that, so once you know H is 192 minus 3W, and you go back and plug H into that equation, so it'll be 2W squared times 192 minus 3W, so this is taking the place of H in the volume equation. So 2W squared times 192 minus 3W. And from here on, this should be a very straightforward question. Basically, you would distribute your 2W squared, you would take the derivative, and set everything equal to 0. So this is a similar question to the one from the last segment, so I'm going to have you finish this one. But when you're ready, you can come back and check the final answer. And so here's the answer to that question. We multiplied everything out to get our volume equation. Then we took the derivative and set that equal to 0. We factored it, and once we got the values, from there once you get W, you can go back and get H. And notice here I did something. I factored out 2 for my volume equation. And as I was taking derivative, I kept the 2 outside. It's like a constant multiple, and I only took the derivative of the inside. You can do it that way, or if you prefer, you can distribute the 2 also, and then take the derivative term by term. Either way you do it, you're going to get with the final answer of W, 384 over 9, and H, which is 64. But when you interpret your final answer, don't forget you have to interpret it as W, comma, 2W, comma, H, right? So if this is your W, roughly 42.67, that's one dimension, and the other side will be 2W, twice that much, 85.34, and H is 64. Okay, so now we're going to do a different type of problem. Enter box example. Here we go. So we have an open box with a square base, and it's supposed to have a volume of 256 centimeter cube. So once again, we're supposed to determine the dimensions of the box, but this time the surface area is to be a minimum. What is the minimum surface area as a follow-up question there? So we have a box, and there's a picture of a box for you right there, a simple box that's open top. Okay, and the volume is given this time. The volume is 256 centimeter cube. And because it says square base, I can call two dimensions x by x, and the height, I called it y this time. So we're supposed to find the dimensions that will minimize the surface area. So this is your typical question where you have a fixed amount of material you want to pack into this box, but you want to do this by using the least amount of material. So you spend least amount of money for the creating the materials for that box. So, one possibility is you could have a very, very shallow box. Okay, that's like one possible option, an extremely shallow box. But typically, that is not going to be your optimal solution. Or you can have a very, very tall and narrow box, and typically that's not going to be your solution. Solution lies somewhere in the middle. So that's why we want to do optimization. We want to find out what X and Y values end up not only containing the volume we're trying to contain, while at the same time minimizing the amount of material that we're using to create the box. So that's our job here. Okay, so it's a minimization question, but the way we begin it is going to be exactly the same as the last few questions. First of all, what is given? We're supposed to create a box, an open box with square base, with a volume of 256 centimeter cubes. So volume has to be 256. What is the volume of this box? X times Y, so X squared Y. That's given to us, and that must equal 256. So in this situation, notice the volume is given. In the last few problems, it was not, right? In the last few problems, the dimensions, length plus girth, something like that was given. Okay, so volume is given. What are we supposed to do? Okay, minimize. We're supposed to have total surface area, which is a minimum. So minimize the surface area. What is the surface area of this box? It's the sum of all the sides. So sum of the areas of all the sides. So this side, this is the area. It's X by Y. And you have basically 4 side panels. Each one is X by Y. Okay, this is the other side. This is the other side. This is the other side. So you have 4XY. Those are the 4 side panels. And then you have the bottom of the container, which is X by X or X squared. So X squared plus 4XY is the surface area of this box. X squared plus 4XY. Read the question carefully. This one was an open box. If it's a closed box, it would be 2X squared because you would have a bottom and you would have a top also. It would be 2X squared plus 4XY. And what are we supposed to do with the surface area? We're supposed to minimize it. So minimize surface area. And notice the surface area function has 2 variables. So given the volume, minimize the surface area. So in this situation, we need to get the surface area in one variable only. So let's use the given information to write one variable in terms of the other. Which variable will be easier to solve for here, do you think? In this equation, which one will be easier to solve for? If you said y, you were correct. Y equals 256 divided by X squared. So from this equation, we can get y equals 256 divided by X squared. And use that now in the surface area equation where you see a y, you can substitute 256 over X squared. So that's what I'm going to do next. So surface area equals X squared plus 4XY, but instead of y, we're going to go and enter 256 over X squared. Now, many times students, when it's time to differentiate this, they try to use the quotient rule, but you really don't need it and you're complicating the problem, I would say, more than necessary. What you can do instead is simplify this quantity, okay? First do 4 times 256. So 4 times 250 would have been 1,000. And 4 times 6 is 24, so 1,024. But also, you can simplify x over x squared. So that will take away one of the x's on the bottom. You're just going to have a single x on the bottom, right? So let's write down the end result. The first x squared is still there. But then the second part, when you multiply 4x times 256 over x squared, there one of the x's cancel out. And you're going to have 1,024 divided by x. Okay. So now we have our surface area simplified and in one variable. Now it's time to differentiate and set it equal to 0, right? We're looking for maximums and minimums. That's our standard procedure, right? So let's differentiate surface area. So SA prime equals derivative of x squared is 2x. Okay, what about derivative of 1,024 over x? How are we going to differentiate that one? Again, we don't need a quotient rule, right? Because we can write that as 1024 times x to the negative 1. And now let's just apply the power rule. So bring the power down, negative 1024 to 1 x to 1 less power, which will be x to the negative 2. And at that point, you can even put in the denominator as division by x squared. Okay, because 1024 times x to the negative 2 is 1024 divided by x squared. Okay, so we have the SA prime, surface area derivative, set it equal to 0. So it looks like we have a bit of a more complicated equation here to solve, right? So not your typical polynomial that you can easily factor, but it's still not too bad. What I'm going to do is I'm going to put the second term on the other side as a positive. So 2x equals 1024 over x squared. And what do you think we could do to solve this equation? What are your thoughts? Okay, if you said multiply both sides by x squared, I would say good idea. Let's do that to get rid of any denominators that are going to cancel on this side. So now we have 2x cubed equals 1024, and then divide by 2, x cubed equals 512. Okay, so x cubed equals 512. At this point, just take a cube root, right, to solve for x. And if you take a cube root, you can put into calculator as like 512 to the power of 1 over 3. That's one way. Or find the cube root sign. I think it's under your math menu. So you will get 8. And units were inches. So 8 inches we're getting for x, one of the dimensions. And to get y, let's go back to one of our previous equations. So right here, y equals 256 over x squared. So do 256 over 8 to the power of second, since x is 8. So the end result will be y is equal to 4 inches. And when you report the dimensions, because it's a box, don't forget to report 3 dimensions, right? It's x by y. So it's going to be 8 by 8 by 4. So it's so the height is not as long as the sides, right? So the height is only 4 for this box. So it's 8 inches by 8 inches by 4 inches. Those are our dimensions. And if they say, what is the surface area? What is the minimum amount of material you're going to need to construct a box, an open box with the required volume? So you need to go back to your surface area equation, and you can go to any form of it, but this one right here is one possibility, or you could go to the very early version, x squared times 4xy. Because we know x, we know y, we can just plug everything in there. X squared plus 4xy. X is 8 squared plus 4xy. 4 times 8 times 4. So 64 plus 16 times 8 gives us 192. And units for area would be square inches. If you want to check it, you could still go back here, take the derivative of surface area prime to get SA double prime, and then you could plug 192 in there, and you're going to find that SA double prime is positive, meaning that it's concave up, meaning that at that point, indeed, we do have a minimum. Okay, so I hope you were able to follow this question. It was a little bit more complicated than the last few, right? But notice that the method that we use to find the minimum of a function is pretty much exactly the same as the method that we use to find the maximum of a function. Basically, get your function in one variable, differentiate and set equal to 0, and don't forget to check it at the end. And here I would like to do one last example on another box problem, but this time it's going to be a box with a cost associated with it. Let me give you a moment to read the question first. So this time we have a closed box, and once again it has a square base, assume it's x by y, and it's supposed to contain a volume of 96 cubic feet. So once again, we know the volume, but the cost associated with creating the box is the top and the bottom is 30 cents per square foot, or $0.30 per square foot. And the sides is $0.20 per square foot. So determine dimensions of the box with the least cost. And what is the lowest cost? So let's begin with our general formula. So the volume is the product of all the dimensions. That's x times y. Surface area, this time it's a closed box, so you have the top and the bottom, so x squared plus x squared, so that's 2x squared, and the 4 side panels, which is plus 4xy. But you also need to consider the cost function. So you cannot just go ahead and minimize the surface area, because the cost of top and bottom is higher than the cost of the sides. And if you put that information in there right away, the beauty of the optimization method is already going to consider those costs within the solution. And because top and bottom are more expensive, that will already be factored in the optimal solution. So it may try to use a little bit less of that, since those are top and bottom is more expensive. So that if we put the cost in from the beginning, all of those things will be factored in our optimal solution. So let's write the cost equation also. So if the surface area is 2x squared plus 4xy, then cost is equal to so 2x squared was the area of top and bottom, but cost per unit area there is 0.30. So it's going to be 0.30 times 2x squared. And then 4xy represents the sum of all the sides, and the cost per unit area for the sides is 0.20. So it's going to be plus 0.20 times 4xy. And in simplified form, I can write this as 0.6x squared plus 0.8xy. So we have our cost function. And once again, it has 2 variables, so we're going to need to get rid of one and write that in terms of the other. And notice that our constraint is the volume. The volume of this box has to be 96. So if you set volume equal to 96, you can solve for y, which is 96 over x squared. So let's take that information, plug in our cost equation right here, and let's go ahead and plug in 96 over x squared. So here we're going to have 0.6x squared plus 0.8x times y, but instead of not y, I'm writing 96 over x squared. So this is a little bit similar to the last problem. It's best to simplify this a little bit, like x over x squared will give you 1 over x, and then we can simplify 0.8 times 96. So I'm going to rewrite everything. So 0.6x squared, that part is not changing, and then plus 0.8 times 96. So I'm getting 76.8 for that. So 76.8, and x over x squared just gave me over x in the denominator. So now that we have our cost function, the cost in one variable only, remember, you don't set the cost equal to 0, right? That is not our goal. Our goal is to find the minimum of the cost function, which is the points where the slope is equal to 0. So set the derivative of the cost function equal to 0. So, and if you need any help differentiating this, remember, you can rewrite 76.8 over x as 76.8 times x to the negative 1 power, and then it'll be easier to differentiate. So please take a moment to do that and come back and check your answer. So if you got 1.2x minus 76.8 divided by x squared, you are correct, because we brought the negative 1 down, subtract 1 from the power, and ultimately I put the negative exponent in the denominator as over x squared. Now set this whole thing equal to 0 and solve for x. This is where, again, it helps to put one of the terms on the other side. So I'm going to add it so it'll be positive, and multiply both sides by x squared. So 1.2x cubed equals 76.8, and then divide both sides by 1.2. So x cubed equals 76.8 divided by 1.2. So go ahead and find what that is, and then take a cube root. So 76.8 divided by 1.2 is 64, and that looks like a perfect cube. And so x will be 4. And what were the units for this question? Everything went in feet. So it will be x is 4 feet. So x by y. So we already know 2 dimensions is going to be 4 and 4. And the third dimension is y. And let's go back and find one of the easy equations to solve for y. I would say it's right here, 96 over x squared. So y equals 96 over 16, x squared, 4 squared is 16. So when we do that, we're going to get 6. Okay, so 6 feet. So the dimensions for the cost with the lowest, basically for the box with the lowest possible cost, is the dimensions should be 4 feet by 4 feet by 6 feet. And they also asked in this problem, they may not always ask you this, but if they said, okay, what is the lowest cost of creating such a box with the given volume and with the given costs associated with unit cost per size and for the bottom and the top. So what is the final cost of the entire box, right? That's the question. Well, we do have a cost equation up there. So I'm going to go back to that equation, and it was right here. This was our cost equation. So 0.30 times 2 times x squared. Actually, let me go to the simplified version of that, which is this one. 0.6 times x squared plus 0.8 times xy. So let me bring it down here. So the cost will be, so 0.6 times x squared plus 0.8 times xy. So if you simplify that, 0.6 times 4 squared plus 0.8 times 4 times 6, you're going to get $28.8. So that is the cost of producing this box, and we're claiming that it is the best you can do, the lowest cost you can do with the given criteria that you had to have the volume as 96 cubic feet. And to check the answer, let's find C double prime. So this is the checking part. So C double prime, so take it from C prime, it's going to be 1.2 minus, bring the negative 2 down, right? So that'll become positive 2 times 76.8, x to the negative 2 power. So 1.2 plus 2 times 76.8 times x to the negative 3, but that's the same as division by x to the third. And at this point, I want to see what happens at this x value that we found, at x equals to 4. So if you plug in there, notice I don't even need to evaluate the actual number because I can already see everything is positive here. When I plug in 4, you're dividing by 64, still it's going to be positive, right? So all I really care about is that this quantity is greater than 0, it's positive. And because it's positive, its second derivative, what does it tell me about concavity? That the function at x equals to 4 is concave up. And if it's concave up, that means at x equals to 4, we have a minimum of the cost function. And therefore, we have confirmed that we're looking for a minimum, and indeed we did find the minimum of the cost function. And one way to check sometimes the answer to these questions is you can actually graph the cost function when you have it in one variable only, like this one right here, 0.6 x squared plus 76.8 over x, and confirm that indeed it does reach the lowest point at the at when x is equal to 4. Alright, so we've done a variety of optimization questions so far, some requiring finding the maximum, some requiring finding the minimums, but the overall process is always the same. And there is still a couple more types of problems I'd like to go over with you, but I'm going to reserve that to the last segment on optimization. See you next time.